this lecture, let's look at Ampere's law. Ampere's law is used to calculate the magnetic field created by various electric currents. So we saw earlier that the magnetic field created by a straight, long current-carrying wire has a different magnitude than that created by a loop or a solenoid, and we need a method by which to solve for the magnetic fields surrounding any sort of current configuration. So that is going to be Ampere's law. Now, this Ampere's law is very similar to Gauss's law. If you remember, we used that to calculate electric fields created by charge distributions. There are differences between them, of course, but the method is very similar. So let's remember Gauss's law. So if we have a charge, and I picked a positive charge, we know that the electric field lines radiate spherically outward from this charge. And then if we're looking for the electric field at a location away from the charge, we know that the electric field will be the same over an entire sphere. So we draw this Gaussian surface, which is a sphere around this charge, and then we use the Gauss's law that says that the electric flux is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. So here we subdivided the sphere into infinitesimal areas that were pierced by electric fields. The cosine of the angle was the angle between the electric field and the area, and then when we summed everything up, we ended up with the electric field times the surface area of a sphere being equal to the charge enclosed, in this case just Q divided by epsilon naught. So we'll use a very similar method for Ampere's law. So here is Ampere's law. It says that the sum of the magnetic field that is parallel to a closed loop is going to be equal to mu naught, which is the permeability of free space, times the current enclosed. So let's see how exactly we apply this. Let's say that we have a current carrying wire, and I'm just going to use a long straight wire, and the current is going up through it. And the question is, what is the magnetic field a distance r away from a current carrying wire? So r away can mean anywhere along a circle around current I. So we draw an Amperian loop at that location. So we have an Amperian loop surrounding the current at radius r, where we're looking for the magnetic field. And then we do the right-hand rule to figure out the direction of the magnetic field based on the direction of the current. So we place our thumb in the direction of the current, wrap our hand around the wire, and end up with a magnetic field circling around in this direction around the wire. Then we're going to look at Ampere's law and see how we have to apply it. Well, we're going to have to add up all of the magnetic fields that are parallel to the loop times the infinitesimal lengths here of the wire. So if we add up over all delta L times B parallels, we're going to make it all the way around the loop. So here is Ampere's law again. And when we add up all of the magnetic fields along this loop, we end up with the entire magnetic field times the circumference of the loop, 2 pi r, and that's equal to mu naught times I enclosed, and in this loop we only have current I. So then when we solve for the magnetic field, we end up with mu naught I divided by 2 pi r, and we know that that is the correct value for the magnetic field for a current carrying wire. We've seen that before.